In this video, we're going to go over the KutaSoftware Infinite Calculus free worksheet continuity. Now, continuity, as applied to a function, think about putting a pencil down and drawing your function. As long as you do not pick the pencil up, that function is continuous over that interval. So in order for a function to be continuous, if we're looking at the function at x equals a, then f of a has to be defined, and the limit of f of x as x approaches a is also equal to f of a. So let's look at number one. In number one, we're to find the intervals on which each function is continuous. So we're going to find the x values of where that function is continuous. In number one, we can see that the function is continuous up until that point when x is equal to 1. For values of x less than 1, this is the piece of the function we're looking at. And then there's a jump, and for values where x is greater than or equal to 1, our function is continuous after that point. So it's continuous up to 1, and then it's continuous from 1 on. So it's continuous over the interval from negative infinity to that point of discontinuity where we have that jump of 1, and because x is not less than or equal to, we're going to use a parenthesis, but from there, 1 is included in the interval in the second half, so we're going to use a bracket from 1 to positive infinity. And when using negative infinity and positive infinity, common practice is to use parentheses. So the function is continuous from negative infinity to 1, then from and including 1 to infinity. Now let's look at number 2. In number 2, you can see that our function is continuous from negative infinity up until that point of discontinuity, which is a removable discontinuity because there is a hole, and then it's continuous after that. So our interval of continuity is from negative infinity to that point of discontinuity, which is x equals 5, so up to 5, and then from 5 to positive infinity, that function is continuous again. So notice that even though f of x is defined, the limit is not equivalent. F of x is equal to 3, but the limit is equal to 1. Therefore, that function is not continuous. In this next part, we're going to find the intervals on which each function is continuous, and it says you may use the provided graph to sketch the function. So let's look at number 3. Number 3 is a piecewise function where we're using 2x minus 10 for values where x is less than 2. This is a linear equation in the form of y equals mx plus b. So our slope m is equal to a positive 2, which we can write as 2 over 1. Our y-intercept b is at negative 10, and that y-intercept is included in the interval because 0 is less than 2. So when x is 0, we're at negative 10 in the y, and using the slope to find that next point, we'll go up 2 in the rise and over 1 in the positive x direction for the run. That's where x is 1 and f of x is equal to negative 8. But I want to go up to that interval of 2, and that's going to be an open circle because x is not included. So going 2 up in the rise and 1 over in the run, that's going to be an open circle around that point, again, because that is not included in the interval. And now I'll draw a line connecting those points. For the rest of my function, f of x is equal to 0. So from 2 on up to infinity, f of x is equal to 0. So I'm going to plot 2, 0, fill that in because that is included in the interval, and then draw a straight line from that point, continuing on in the positive direction. So you can see there is a jump at x equals 2. And because the limit of f of x as x approaches 2 does not exist, we have a point of discontinuity. Therefore, our interval is not continuous at x equals 2. But it is continuous from negative infinity to that point 2, and then x equals 2 is included in the next interval, so I'm going to use a bracket to show that it is then continuous from 2 to positive infinity. Those are the intervals of continuity for number 3. Now on to number 4. For number 4, I can tell the point of discontinuity right away, and that will help me solve for my interval. Remember, we cannot divide by 0, so when this denominator equals 0, that x value is a point of discontinuity. So x plus 1 equals 0 when, subtracting 1 from both sides, x equals negative 1. So when x equals negative 1, I have a point of discontinuity. So from negative infinity to negative 1, and then from negative 1 to infinity, that is where my function is continuous. And let's go ahead and double check with a graphing calculator. Our function is x squared minus x minus 2 all over x plus 1. So you can see that we have a line that intersects the y-axis at 0, negative 2, and intersects the x-axis at 2, 0, but at negative 1, our function is undefined. So quickly, I'll plot 0, negative 2, and 2, 0, and our point of discontinuity was at negative 1, but as x approaches negative 1, f of x appears to be approaching negative 3. So at the point negative 1, negative 3, we will have an open circle to show that point of discontinuity. Now I'll draw my line. So here's a graph of my function clearly showing that point of discontinuity. And double checking the interval in which the function is continuous, we're coming from negative infinity up to that point of negative 1 in the x, and then from that point of negative 1 in the x on until infinity. Let's continue on to the second page. For numbers 5 through 8, we're finding the intervals on which each function is continuous, but in this section we're not going to be graphing. But we know how to find those points of discontinuity. Let's look at 5. 5 is not continuous when that denominator equals 0. So when 2x plus 4 equals 0, we have a point of discontinuity. So if I subtract 4 from both sides, I'll have that 2x equals negative 4, and then dividing both sides by 2, I'll get x equal to negative 2. So when x is equal to negative 2, I have a point of discontinuity. But from negative infinity up until that point negative 2, my function is continuous. And then from negative 2 on to positive infinity, my function is continuous. So those are the intervals on which my function is continuous. Let's move on to number 6. In number 6, we have a piecewise function. Now, in order for this function to be continuous over all intervals, at x equals 0, each piece of our function must be continuous, because that's the point in which the equations of my function change. So I'm going to plug 0 in for x in my first piece, so negative, or the opposite, of 0 over 2 minus 7 over 2, that's going to give me a negative 7 halves. So I need to see if this second function equals negative 7 halves when I plug in x for 0. So the opposite of 0 squared plus 2 times 0 minus 2, that's going to equal a negative 2. So because negative 7 halves does not equal negative 2, then my function is not continuous at that point. When x equals 0, we have a point of discontinuity. So from negative infinity to 0, our function is continuous. And remember that function value at 0 is included. So I'm going to use a bracket. And then from 0, where the 0 is not included, to infinity, our function is continuous again. So in number 6, those are the intervals on which the function is continuous. Now on to number 7. Our function is not continuous when x plus 3 equals 0. So x plus 3 equals 0 when, if I subtract 3 from both sides, x equals negative 3. So my function is continuous from negative infinity to negative 3, and then from negative 3 to positive infinity. That's my solution in number 7. Now for the last part in this section, number 8. For number 8, our function has a point of discontinuity when x plus 2 equals 0. So I'm going to subtract 2 from both sides to get that x equals negative 2. So my point of discontinuity is at x equals negative 2. That means from negative infinity to negative 2 my function is continuous, and then again from negative 2 to positive infinity my function is continuous. And that's my solution in number 8. Also, I want to point out in number 8 that we are able to factor the numerator and cancel out that denominator with one of the factors of the numerator. However, regardless of whether this discontinuity is essential or removable, does not affect the intervals on which the function is continuous. If it's removable discontinuity at that point, the function will not be continuous at that point. And if it's essential discontinuity at that point, the function will also not be continuous at that point. So again, whether it's removable or essential does not affect the intervals on which that function is continuous. We just know that it is not continuous at that point. For numbers 9 through 14, we're going to determine if the function is continuous. If the function is not continuous, we're going to find the x-axis location and classify the discontinuity. So remember, essential discontinuities cannot be factored out. Removable discontinuities can. So in number 9, there's no way to simplify this in order to remove that discontinuity from the denominator. So we will have an essential discontinuity and that occurs at x equals, well, we have to find out when this denominator is equal to 0. 2x plus 4 equals 0 when, subtracting 4 from both sides, we have 2x equals negative 4, and when I divide both sides by 2, I get that x equals negative 2. So there's an essential discontinuity at x equals negative 2. And number 10, I can factor this denominator. So I'll get x plus 1 in my numerator, and that's going to be all over what multiplies to give me negative 2 and adds to give me negative 1. That's going to be a negative 2 and a positive 1. So I'll have x minus 2 times x plus 1. Now, x minus 2 cannot be canceled out. So it is an essential discontinuity when x minus 2 equals 0 because it cannot be canceled out. And the value of x that makes x minus 2 0 is a positive 2 because 2 minus 2 is 0. So we have an essential discontinuity at x equals 2, and because we can cancel out x plus 1, that's going to be a removable discontinuity. So then we will have a removable discontinuity at, well, we need to see when x plus 1 equals 0 and x plus 1 equals 0 when x is equal to negative 1. So that's a removable discontinuity at x equals negative 1. So number 10 is a great example of where we have an essential discontinuity and a removable discontinuity. Essential at x equals 2 and removable at x equals negative 1. Now, number 11, we cannot factor that denominator because our roots will be complex and imaginary numbers. So let's go ahead and graph this so you can see that the function is continuous. There are no points of discontinuity. So I'll graph x plus 1 all over x squared plus x plus 1. Now that I've written in this function, I'll expand this out a little bit so you can see the graph, and you can see that there are no points of discontinuity along this function. Therefore, in number 11, our function is continuous. Let's move on to number 12. We cannot factor number 12 in order to cancel out x minus 1. Therefore, we're going to have an essential discontinuity at that point, and that x value that will make the denominator equal to 0 is a positive 1. So when x is equal to 1, we have an essential discontinuity. And number 13, we're looking at a piecewise function. In order for this function to be continuous, when x equals 0, f of x needs to equal a positive 3. So I'm going to take 0 and plug it into my first piece of the function to see if that equals 3. If it does, my function is continuous. So I'll have 0 squared minus 4 times 0 plus 3, which 0 squared is 0, 4 times 0 is 0, and I add 3 to that, I do indeed get 3. So because 3 is equal to 3, my function is continuous. Now in number 14, again, we have a piecewise function. However, in the case of this piecewise function, our function is equal to negative x squared for values where x is less than 1 and values where x is greater than 1. So we just need to see if at 1, that function equals 0. Because f of 1 is 0, so we need to see if this first part of the function is also 0 at x equals 1. So plugging 1 in for x, we'll get negative 1 squared, which equals a negative 1. So because negative 1 does not equal 0, our function is not continuous at that point. There will be a hole. Therefore, we have removable discontinuity at x equals 1. Now onto the critical thinking questions. For number 15, it says to give an example of a function with discontinuities at x equals 1, 2, and 3. Now it doesn't say what type of function, so you could even do a piecewise function here if you want. However, I'll go ahead and just make values in the denominator that equal 0 when x is 1, 2, and 3. So my numerator, I'm just going to leave very simple. That's going to be 1. Now, if x equals 1, in my denominator, I want x minus something equal to 0. And that's going to be x minus 1, because when x is 1, that's a point of discontinuity. I'm then going to multiply that by a binomial that makes plugging 2 in for x equal to 0, and that's going to be x minus 2. If I plug 2 in for x, I'll have 0, and 0 times any number is 0. That's why I'm multiplying these together. And then finally, I'm going to multiply by x minus 3. Plugging 3 in for x, I'll get 0 in my denominator, and 0 times any number is 0. So plugging 1 in, I'll get 0, and then I'm still multiplying that to x minus 2 times x minus 3, but 0 times any number is 0. Plugging 2 in, I'll get 0, but a number times 0 times another number is still 0. So I still have 0 in my denominator, and then, like I said, plugging 3 in, I'll get 0, and any number times 0 is 0. Therefore, this is an example of a function with discontinuities at x equals 1, 2, and 3. Essential discontinuities. If I wanted one of them to be a removable discontinuity, I would have to write that same binomial in the numerator. Then that would give me a removable discontinuity because I would be able to cancel it out. But it didn't specify whether they had to be removable or essential. Let's continue on to number 16. Number 16 says, of the 6 basic trigonometric functions, which are continuous over all real numbers? Which are not? And what are the types of discontinuities? So for this, it'll be helpful to look at a graph. So I'm going to graph these on my graphing calculator. So let's start off with sine. The sine of x is continuous over all real numbers. It is just oscillating. The cosine of x is also continuous over all real numbers. Next, we'll look at the secant. And you can see that the secant of x is not continuous. It has essential discontinuities. Next, we'll look at the cosecant. And you can see that the secant of x is not continuous. It has essential discontinuities. Next, we'll look at the cosecant. And you can see that the secant of x is not continuous. It has essential discontinuities. Next, we'll look at the cosecant. And you can see that the secant of x is not continuous. It has essential discontinuities. And now our graph's a little crowded. So the sine of x and cosine of x are both continuous. So I'll go ahead and exit out of those and write that in real quick. So the cosecant of x also has removable discontinuities. Next is the tangent of x, which you can see also has essential discontinuities. And then lastly, the cotangent of x, that also has essential discontinuities. So we're not continuous on the secant, the cosecant, the tangent, and the cotangent, and those are all essential discontinuities. Now the values of those discontinuities differ, but that's not what the question asks. It's just asking what type of discontinuities were there. They were all essential. And with that, we wrap up the free continuity worksheet on the KutaSoftware website. If you have any questions, as always, put them in the comments below and support me by liking, subscribing, and sharing this video. Also, if you feel so inclined, I encourage you to become a patron. Go to my Patreon page to sign up and pledge. I'll leave a link in the description below.